Did you know that a data scientist can trick you with AI? Let me teach you how to avoid it in a few minutes. Imagine you got super rich and you started a bank. Then you hired a data scientist to build a fraud detection system over the customer transaction. You took the data of the transactions and handed it to the data scientist. The data scientist splits the transactions data into train test data. He trains a model and delivers to you a 99.5% accuracy model. Now you have a problem. Did you spot the mistakes here? Pause and comment them down below if you do. And if you don't worry, I'm here to save you. That unprofessional data scientist made huge mistakes. First, the data distribution. In a real-life scenario, less than 1% of all transactions are fraud. So if you design a naive model that takes every transaction and always predict not fraud, you will get a similar accuracy. So to overcome this, you need your classes ratios to be equal as much as possible in your train and test data. For that, you have some options. First, oversampling, which is repeating the minority class for that target. Second, undersampling, which is reducing the number of sampling in the minority class. But those solutions may lead to overfitting, noise amplification, and loss of information. There are some more intelligent solutions, like smooth and add a scene, which generates synthetic examples by interpolating between existing minority class examples. With those approaches, you didn't just get more meaningful accuracies and training, but also you prevented your model from being biased for the majority class as most of the machine learning models would do. So now your data scientist splits the data with balanced ratios and distributions. Then he gave you a 99% accuracy model. What do you think is missing here? In fact, that's not enough to evaluate your model. Model doesn't clearly predict fraud or not fraud. Instead, model predicts probabilities between 0 and 1, but typically classified transactions as fraud or not fraud based on threshold, which is by default is 0.5. Let's explore how adjusting this threshold can affect your outcomes first. But remember, our priority here is to avoid frauds as much as possible, even if it blocks some legitimate transactions, rather than letting some fraud transactions complete. So let's change that threshold and see what happens. Once with a value closer to 1 and one with a value closer to 0. For both models, the prediction that is greater than a threshold would be considered 1 or positive, and 0 or not fraud for the left side. Ironically, those two models have the same accuracy value. Let me explain more the difference between them. In both scenarios, the model has two ambiguous instances. The first model will classify both of them as 0 or not fraud, letting the fraud transaction pass in favor of not blocking a legitimate transaction. But the second model will classify both of them as 1 or fraud, which blocking a legitimate transaction in favor of not letting a fraud transaction go. Eventually, your choice of model will be based on how much you understand of your business needs and your decision with those gray areas. You will need to define a cost that a business can afford with your model. In our case, blocking a legitimate transaction is better than letting a fraud transaction to complete. Another example here. Assuming you're building a model to predict drug usage for a person based on some medical tests. This example will be the opposite of our bank example. You might want a drug user to get away with it in favor of not ruining an innocent person's record and letting them having it for the rest of their lives. Now let's get back to our example. So instead of just measuring the accuracy of the model, we need something different to tell us the story with numbers. For our bank example as a binary classification model, we will build a 2x2 matrix for our predictions and the ground truth values. Then add the number of true and false positive predictions accordingly, as true positive, false positive, true negative, and false negative. These values help us understand more the model accuracy beyond just correct and incorrect predictions. And this is the confusion metric that we will use to get more metrics for us. First metric is precision, which is model sensitivity, or the proportion of positive predictions that are actually correct. And it's preferred to maximize this metric in examples like drug tests. The way it works is that it gives penalty for the false positives. The more false positive you have, the less precision you will get. Second metric is recall, which is the proportion of actual positive cases that were correctly identified. And is preferred to maximize this metric for examples like medical diagnosis, where missing a disease could be dangerous. And it works exactly like a precision, while the penalty is on the false negatives. Now we need to adjust our threshold to optimize recall and precision based on our business needs. There are other metrics, but I will only mention one important now, which is F1 score. which gives the harmonic meaning between precision and recall. Now we can better understand our model, but there is a good question. What if we have more than one model? How can we pick one? The values of precision and recall aren't really enough here to make a decision. This doesn't tell you how much confidence a model can distinguish between classes. Let me explain it, and I promise to keep it simple. For each model, the data scientist has to generate the ROC curve. For each model, the data scientist has to generate the ROC curve. At a very basic knowledge level, you don't need to know how it's generated. But long story short, it shows how your model's different thresholds can reflect on the trade-off of true positive rate and false positive rate. And each point represents those values as a different threshold. A perfect model at a specific threshold would be at the very top left corner of the ROC curve, meaning it correctly identifies all positives without any false positives. In summary, the ROC curve helps you to assess how a model can distinguish between classes by adjusting the classification threshold. And we do that by calculating the area under those ROC curves, or AUC, with AUC closer to 1 indicating a perfect model, while an AUC of 0.5 representing a very random model. At this point, we can compare the general performance of our models with the area under those ROC curves, or AUC, with proper data distribution. And now, congratulations! Now you can start your bank without scammers. I hope this video helps you avoid common mistakes in machine learning model evaluation. If you found this helpful, feel free to leave a like, comment, and share it with your connections. And until the next video, peace.